In un contesto di guerra elettronica, e comunque in un contesto di guerra, ci possono essere anche tutte le intenzioni per fare in modo che anche la ricognizione da parte del nemico sia offuscata. Quindi che grado di resistenza ha l'interferenza così?
So the question is how much is the level of resistance against the electromagnetic interference with respect to external source?
From a hardware point of view?
Yes, from the hardware point of view.
For ourselves, sorry, I'm getting a microphone signal. From ourselves, we don't get involved in the hardware part. There's other bits of Hexagon that do work with hardware and anti-jamming and so on, if it's GPS or GNSS involved. For ourselves, we're working with downstream from that, so we're working with the data, not necessarily the hardware itself. You're on that yet, so.
Hexagon sì, fondamentalmente la parte software, l'integrazione del software, con, non la parte hardware. Ok, adesso D.W.Holcomb ci parlerà farà un focus sul SAR, quindi anche in questo caso sintetica Aperture Radar. Oggi, nella giornata di oggi possiamo dire che il SAR è il trend topic, abbiamo già visto il sistema di Egeos e adesso D.W.Holcomb ci parlerà, farà un focus sulla parte Hexagon, come si gestiscono le immagini SAR. Grazie D.W.
Okay, is this working? Is this turned on?
Yes.
No? Ah.
There are buttons? Aha.
Yeah.
Button up.
Okay?
Come on, come on.
Yeah.
I don't usually need one anyhow.
But you did, you make it, yes.
Okay. Well, hello, ladies and gentlemen. It's a pleasure for me to be here again. And I say again because I've been to Italy many times. I've actually been coming to Europe for over 30 years, representing ERDAS, largely in the world of radar image processing. I've come here many times to train various defense analysts in various countries here. So I want to talk today about some of the applications of SAR data. We've talked a lot about how we integrate this data in some of our applications, but I want to show you why we do that. And I'm actually in Europe now for over a month on this particular trip because radar data is being vastly underutilized. And that's kind of a shame because, for one, we have Sentinel-1 data, which is free. But I understand it's being underutilized because, to a lot of people, it's very difficult to understand. It's not an optical image. It's a very different kind of image. And also, with radar imagery, we can do a lot of image processing that extracts information. It's something you cannot do with your eye. It's something that no other sensor can do. And I want to introduce you to some of these applications that we use it for so you'll understand the sort of information that can be extracted and given to your analyst. Now, a real important point is that a radar sensor is very different from an optical sensor. They respond to very, very different phenomenology. So if you have an optical image of your target and a radar image of your target, you have two very different looks from a very scientific and physical level of what that target is. Obviously, aids your interpretation there. I should mention, I'm actually an image analyst scientist, so I may get a little bit too scientific here. Okay, the one thing most people do seem to know about radar data is that it penetrates. Right, so here we're looking at an optical image in the Sudan. There's our radar image. So in this instance, the beam is penetrating through the cover surface, and we're seeing the bedrock. Now, this particular project was done because we had to find water for these refugee camps. We wanted to understand the bedrock structure so we could do a geologic mapping and decide where to drill. Here's another example. Here we're looking at the optical image. Here we're looking at the radar image. Okay? The optical image is giving us a surface reflection. The radar image is penetrating that surface and showing us metal objects. Radar is very sensitive to metal. That's another reason it's important to you gentlemen. So I have here a subsurface mapping of oil pipes, water pipes, power lines, all the infrastructure that supports this refinery. Again, this was a real project because after the Iraq War, many of these refineries and production centers were totally destroyed, including their records, and we actually had to go back and rediscover some of their lost infrastructure. Another example, radar sees through clouds, sees through smoke. A lot of applications for radar imagery are very real time. We have a problem, we need information now. We can't wait till the sun comes up. So as you can see here, in this particular emergency, optical imagery couldn't really show us the details on the ground. Radar imagery could. Okay, this is my underlying strategy I've finally put together after 4 decades of doing this. And the important word here is radar-derived information. People, like yourselves, don't really want to see radar data. You just want the information. So the software now is very much focused on rapid information extraction and disseminate that information to the people who need it rapidly. And I would mention, for example, one facility we put up in Tromsø, they had 15 minutes from the time they got the data to the time they sent the results to the people who needed it. 15 minutes, or it was useless. This is an example of one of the radar workstations that we have. A couple things I would just point out here. One is, as has been brought up several times, particularly by my colleague here at EGIOS, we don't import data anymore. This data here is in the original format. We simply ingest it. When we ingest radar data, we ingest the pixel values and all the supporting metadata. With radar, the metadata is real important. In this particular instance, we take that metadata, we construct an imaging model, and we automatically georeference it on the fly. So when you read this radar image into the Imagine viewer, it's automatically georeferenced. So you can see here I have my cursor, I got my latitude and longitude. Another thing here I'll talk about a little bit. You've probably noticed this radar imagery is always gray. It's usually grayscale. We only have one band. It's very suboptimal for analysts to look at gray image. It's very tiring on their eyes. So this particular little application I have right here was actually developed in conjunction with German defense, because what we want to do is, as we read this imagery from the raw format into the viewer, we geocode it and we automatically apply 3 enhancements and layer stack those into a color image. And obviously, this is a whole lot more pleasant to look at than a grayscale image. And this is done on the fly. If I zoom into this image, it automatically recalculates, and within a second or two, you see the higher resolution image, always going back to the original data. So we keep our highest resolution at all times. Okay, I'm going to talk first about the magnitude layer. This is another thing that radar has that other sensors just don't have. Every pixel has 2 values. We have the magnitude, which is what optical imagery has. How intense was that return of signal? But we also record the phase of that signal, okay? When that radar wave came back to the antenna, did it hit on the peak? Did it hit on the trough? Was it somewhere in between? By doing that, we can actually do measurements at the sub-wavelength scale, okay? So if your wavelength is 2.5 centimeters, I can easily detect things at a 0.5 centimeter scale. Very few other sensors can do that. LiDAR can. It's expensive and you can't do it from space. So I'm going to talk first about the magnitude layer, and then we'll talk about that phase layer. I have put a lot of work. Actually, you're looking at 2023. So this will be the next release. This is on my computer. You don't have it yet. You'll get it in 6 months or whatever. But for the new software, I've put a lot of effort into the change detection module, because change detection is so important, particularly in your world. I'll talk about some of the changes, but I don't have time to talk about all of this stuff. Normally, when I train a analyst, I have a 5-day training class. That's what it takes to really teach an analyst to use our software optimally. But just very quickly, I want to talk about one of these newest algorithms that I have in there, because this is single image change detection. Normally with change detection you have 2 images. before and after, you're looking for change. In this particular case, what we do is we take our radar image, and as people have said, it's in raster space, it's in map space. I actually convert this image into time space. I then separate it into two separate time categories and then convert those back into image space. I know it sounds a bunch of craziness, but that's one of the powers of radar imagery. We can do a lot of mathematical processing very quickly that extracts information that there is no other way to do. So there is an example image. This was Japan because I developed this for Japanese Defense Forces. And you can see here a couple of ships. Ships are very easy to see on radar data. I talk about that a lot. I don't know if I have time for it today. But by running this algorithm, you'll see it suddenly change. We have some color here in these images. Take a closer look at that. That ship has now been separated into two halves. And all of my change detection is color-coded into this paradigm we have. Red has fled, blue is new. All change detection is color-coded that way in Imagine. So what this is telling me, red has fled. That means in the first half of the time, this is where the ship was, but now it's gone. Blue is new. In the second half of the time, the ship was in this position. So I can tell that this ship was moving and is moving in this direction. Right? And that should agree with the AIS information, unless they're jamming the AIS or they're giving false AIS information. So this is just one of the new change detection tools we developed. There's the original. There it is, separated into two pieces. Done in time space. You can't do this with optical data. And also, in all of the change detection algorithms, I try to push it all the way through into a shape file. A shape file is a very compact information storage package that's very standardized, and then once you have your change in a shape file, you can take this and put it on top of an optical image, put it on top of a map. You can do other things with it. So as I said, I want to extract information and get that information to somebody who needs it. That's where this software goes. Am I going right here? Okay. Also, I have a package of algorithms here, or techniques, where I can, as I already mentioned once, I can do things to the image on the fly as I read it into the viewer. Okay? So just by selecting this right here, I automatically convert my grayscale into whatever I've selected. And I won't have time to go into all of it, but I've already showed you this one I call Auto Enhance. That's the one that I developed with German Defense. Takes that grayscale image, does 3 enhancements, layer stacks them together. From your point of view, you just push the button and it changes right before your eyes. There's an example. We have already looked at one. This is where I was testing Capitolo. Obviously, I have to work very closely with all the data suppliers to make sure that we ingest their data. We bring in the pixel values, magnitude and phase, and we bring in all the metadata we need to do the analysis we need. So I was just testing the Capitolo data set with this real-time enhancement. This is the one I call speckle suppression. Speckle is the thing that makes it so difficult or unpleasant for people to work with radar data, because you see it has this, what we call salt and pepper effect. Bright pixels, dark pixels. Now that's caused because we're working with these waves and they're interfering. We won't go into the science. But for people who want to visually, or even with an algorithm, extract information, that speckle noise creates problems. So we have lots of algorithms that will convert this speckly image into this, where we've suppressed that speckle. Now you've got to be careful when you do that, right? If you see a bright pixel out there, is that bright pixel a speckle or is that a tank? So you can't just push the button and wipe everything away. You've got to be careful with what you do. And I have a workstation that allows you to do that very quickly. I'll try to talk about that a little bit. That's my despeckle operator. This is a real-time change detection. As I said, all change detection in Imagine is encoded. Red has fled, red is old, blue is new. So in this particular case, I was actually working on a mine in Arizona, but I simply input 2 images into the system. Again, these are both pause. You just input the scenes, push the button, and on the fly it creates this image. Because when I imported this metadata, I also imported the date. So I know which scene is new and which scene is old. So I can make this change detection image in 2 seconds. This is really good because a lot of analysts are maybe having to monitor 20, 30, 40 sites, possibly worldwide, and they need to decide where to spend their time and where not to. So to have this, what I call a quick and dirty change detection, as soon as they get a new image, they compare with the old image and see, is there any change worth wasting time on, or has nothing really happened there? And if changes happen, they know immediately where to focus onto it. And as I've said, you can zoom down into this, and because I'm going back to the raw data, I always get the original pixels, highest radiometric and geometric precision. I won't talk about these a whole lot, but these are a couple other little tricks that I have in my workstation. You know, mostly you've been seeing this grayscale image, right? As I said, that's the magnitude. That's how we normally look at radar images. But I have a couple other tools here that allow me to look at it other ways. One thing I do is I do what I call a level slice. In other words, I say, this is not a radar image, this is a pseudocolor image. And I want to manipulate it as a pseudocolor image. And so, on the fly, push the button, it converts the radar image into a pseudocolor image, gives me a histogram of that image, and using these little sliders down here, I can break that image into 3 separate bins and give each bin a different color. So I can optimally color encode a radar scene, emphasizing the things I want to emphasize. Now in this particular case, this was a flood event out in Colorado a few years ago. And you can see, I very quickly shown, here's the river, here's where the river's overflow, here's some flooded fields out here. Very quickly, operational information. And of course, in a hurricane or a flood, getting the information fast is important. Where the flood was yesterday is totally irrelevant. Here, we're using the tool for some other purposes. We've done a lot of work with Canadian Defence over the past couple of years on land-water separation because they have so much territory and so much coastline with no population around. They can't monitor all this stuff continuously with humans. So we're trying to automatically allow them to do this sort of land-water separation. This was another project here. I'm mapping oil slicks because normally you can see the water has some brightness to it because there's waves, the wind is blowing, but oil quells the surface of the water, okay? Just a little bit. But radar is very sensitive to that micro relief, right? And so, since the oil has suppressed that ripple on the surface, we can map these oil slicks very quickly. And again, I mean very quickly. We know where the ships are because ships are easy to see in radar data, okay? We can get their AIS information, and we can discuss with this person why this oil slick is in his track. So this system was put together for the European Maritime Safety Agency, EMSA. This system's up in Tromsø. This is the one I talked about. They have 15 minutes from the time they get the image to get some coordinates into the airport to go out and investigate this. Okay, I'm going to talk about a couple of real projects here. I'm going to show you why I have this kind of software. This is what I call the radar analyst's nightmare. This is 2 radar scenes. The first one was taken at some point in time. The second one was taken the day after somebody fired a missile at one of our ships out in the Arabian Gulf, Persian Gulf, whatever you want to call it. Very, very difficult, probably impossible for an analyst to look at these 2 images and find change, right? That's why I want to geocode it on the fly into map space. I want to color enhance it. I need to, all right, okay. And there is the quick and dirty change detection map I can make. Just input 2 images, push the button, and I've suddenly got this color-coded map of change between these 2 images. And I won't have time to go into each one of these areas, but the airfield's important, the harbor's important, the administration building's important. one example I always make is I was doing a study somewhere in the South Pacific, and I noticed one day that the parking lot over here was really full. And I just looked at the date, and it was a Sunday. And I thought, either it's the Commandant's birthday, or there's some kind of important meeting that took place on that Sunday, right? So that's just, analyzing the administration area. But what I want to talk about is this launch pad. That's what was interesting to us, because somebody launched the missile. This is an example of our despeckle, where I've taken that radar image and despeckled it. This is probably too much. I've gone all the way up to 100 here, but I have a little button right here. I can go 10, 20, 30, 40, 50, and almost as fast as you can change those numbers, it re-despeckles it on the fly. So within 1 minute, 2 minutes, I can optimally despeckle for my application, right? What kind of product am I trying to make? What size target am I trying to detect? That's why, this is a real-time workstation. Another thing that's relevant to you is I have up here the ability to emphasize or de-emphasize point targets, right? When you despeckle, you may be very interested in point targets. You may not really care about them, so that's something you can set there. But in the end, this is the kind of product I can make. This product right here, it's a change detection image, and you can see here's some blue. Blue is new, here's some red, red is lead, here's a blue is new over here. It's a little bit suboptimum. The reason is that quick and dirty change detection just uses the sensor models. And radar sensor models are very accurate. You may know a lot of people use radar imagery to georeference their optical imagery, because the radar sensor model is much more precise on the ground. We usually like to be within 1 or 2 pixels of precise on the ground. But nevertheless, if we're off by 1 or 2 pixels, purple is kind of red and blue. So that's where we have a red pixel and a blue pixel side by side, because things are not perfectly co-registered. Okay. We have software within Imagine for precisely co-registering radar images. And when I say precise, we co-register radar images at 1/100th of a pixel. 1/10 in latitude and 1/10 in longitude. 1/100th of a pixel. Optical data comes nowhere near that. With optical data, you'd be happy to be within half a pixel. You'd be real happy. We go down to 100th of a pixel. By precisely co-registering this stuff, you see I get rid of that purple. Everything is now nicely lined up, and I can see my blue is new, red has fled. Now this is the missile launch site. So the fact that things have changed over here could be significant, since we know a missile was launched from somewhere. As I said, we push that into a shape file. This is concentrated information that you can pass up your chain of command, or that your analyst would pass up to you, let's say. And we have a nice color-coded change here. You can put this on top of a map, on top of an optical image. If you decide that this is kind of interesting, this is kind of interesting, you have precise coordinates to target an optical camera, operational information. That's all I can talk about. We do obviously have this thing that people call artificial intelligence. I call it deep learning, because as people have said, we have to train these things extensively. It's not an artificial intelligence like we have. It's really more of a training process. This is what the GUI looks like. This is what my GUI looks like. All this stuff isn't deployed yet. But from your point of view, you would have this kind of a GUI. You would just input your image, tell it what you want, give it an output name, and then push the button. Now, again, in development, I have the ability to keep it as a probability map. Because all detections are a probability, right? Everything is not just black and white. There's going to be things that are, is that a target or is it not a target? So I do have the ability to keep this as a probability map and make my own decision, where's the threshold target, not a target. Just to give you an example, this is one of my standard test areas. It's Phoenix, Arizona. I like it because I have ground control points there. I've been there many times. I have a lot of ground truth there. And it has sort of everything, right? I've got a dense urban area here. I've got sort of a suburban, agriculture kind of area. I've got mountains. I've got floodplains. the image has everything I want for testing point of view. I'm going to take a look at my road extraction algorithm. Now this also was developed for Canadian Defence Forces because they have all this area that they can't monitor. There's people up there, but not a whole lot. Anyhow, that is the road vector map that would be extracted from this scene, automatically. And you can see, in some areas, like down in here where there's not a lot of roads, it's probably a pretty good road map. You get up into here, you've got buildings, you've got trees, you've got shrubs, you've got cars. It's very, very difficult for an algorithm to devolve all of that complexity. But there's a good example of what I've seen in a dense urban area. So I've got pretty good mapping of the roads. You know, I could probably guess that this road may go through here, right? This road probably goes through here. That's what I get automatically. And it's a whole lot of information that I get real fast. And then if you need it more precise, someone could hand edit this. But someone could not start from scratch from that radar image and hand map all these. I guess you could give a student the job. This was another one. This is railroad extraction. This one actually amazed even me. You can see I was looking at a dense urban area and how cleanly I pulled out this railroad. Now we're looking here at the probability map. Remember I said I can make a probability map or I can say a yes or no map. Here I made a probability map. I was looking where should I set my threshold. So the red and green are just different probabilities that it's a railroad. But you can see it did a pretty good job. My main false positive down here is the Autobahn. And it probably has a lot of metal rails and all kinds of stuff. So okay, I can understand a false positive there. But clearly a very clean job of railroad extraction. So that's the example of what I call deep learning artificial intelligence. So as we've said, it can help you. It doesn't do miracles. It doesn't make decisions. And we have a deep learning despeckle. Right there, yeah. So you can see here's that speckle noise that irritates everybody, including the algorithms, cleaned up a little bit. Now the nice thing about the deep learning despeckle is it's fully automatic. So you can set this up so that the data is automatically downloaded onto your server and despeckled while you're at home in bed. Okay? You come into work in the morning and it's already done for you. This was land use classification. It's okay, I'm not satisfied with it. I'm going to talk real quickly here about phase. I don't have a lot of time left, but I said every pixel has a phase and a magnitude. Now, see, there's the phase. You can't look at the phase and interpret it any. So this is all done automatically. I have lots of change detection stuff working on phase. I can't go into a whole lot, but you can see I can put in these grayscale images and get out all kinds of color-coded information. This is actually a Panama Canal. And imagine when you run coherence change, you don't just get the standard grayscale change map. You can get any of these other products. This one here is a particular favorite because that does a change detection in magnitude, a change detection in phase, and stacks those together. So this is a double change detection actually, very powerful image. Let's talk about how I use that sort of thing. This was a facility in Iran. The Americans were saying it was a centrifuge area. The Iranians were saying it wasn't. The European Union was trying to decide what to do. This project was, what, half a dozen years ago. This was a very important project. For the European Union to put sanctions on Iran was a multi-billion-dollar decision. Okay? So we had to have good information. This is what a typical optical image of this area looks like. To me, as a radar analyst, it's very flat. It doesn't give me the kind of information that a radar image will. Radar image is, giving off its own radar beam. Here's my look direction. I know how to interpret that. I won't have time, but for one simple example, there's the front of a ridge. There's the back side of a ridge. Right? So I can already interpret topography here. And I can interpret things like, here's a dark line. I know that's a road. Here's where the bulldozer pushed all the dirt. I don't have time, I'm sorry. But this is that product I talked about, the double change detection. So I could take two radar images, look for the change in the magnitude, the change in the phase, and layer stack. And I instantly have color-coded information I can start interpreting. And you can see yourself a lot of real simple things. There's a lot of activity here, right? Cars are driving around, lowering the coherence. But look at this. Nobody gets past this point. There's a control point right here, right? here's a wall here with a metal fence along it. Again, don't have time to go into it. There's my magnitude change detection. That's what we do in optical data. There's my phase change detection, right? A whole lot more information. That's why I like this phase. And we're talking about change at the sub-wavelength scale. Change at the centimeter scale. Coherence, the way it's normally displayed, is suboptimal because bright means no change. The coherence is high. Dark is where the change is. Coherence was lost, something changed. But your eye doesn't work that way. Your eye is sensitive to bright, not dark. So this is not optimum. So I can reverse the coherence. Now, change is bright. And as one simple example, all of a sudden this kind of jumps to my eye. Right? It's over here. It's not magic. But I made the image more visually interpretable just by inverting the contrast. But you can see there's a lot of stuff out here. Cars are driving around, the goats are eating grass, whatever's going on here. So I can also doing non-linear inversion. So I said, I want to see change, or I want to see important change. I got to speed up. Okay, as we went through this study, we could do these things over different periods of time, right? October to January, Jan, Feb. I can make these kind of inverse, coherence, temporal analysis. I'm putting these images together. And then I can layer stack them. So I now have a lot of color-coded information. I can't go into it a whole lot, but it's real obvious once you look at this stuff. Every vehicle comes to right here. There's two spots right here that they have to be built with metal roofs. And then everyone has to drive along this ridge, come along here. There's a second point here they have to interact with. Very difficult to access this facility. It doesn't look to me like a Walmart. And at the same time, I have a lot of color-coded information. I watched through the imagery. I watched them slowly build this road. A metal line appeared around it, probably a fence. There was a lot of activity at some of these node points. I think probably guard towers were built. Again, we might have auxiliary information, optical information, but this is a nice color-coded map of activity in this area. Now, here's one of the magic things. When this was presented to the European Union, they went and talked to the Iranians. The Iranians said, we're building a truck factory out here. Looked a little suspicious, but anyhow, I took this same data. The data that I used to make the color-coded multi-temporal change, I took the same data and ran it through different software and did a different process on it and made a digital elevation model. Exact same data, different mathematical process. And then I took and put my color-coded change on top of the digital elevation map. And the question simply became, why are you building a truck factory into the side of a mountain? Difficult to answer that question. But also this is operational in the sense of if we want to get an optical camera to take a look, we know we're going to have to look from this direction, right? We can't see from here. We can't see from here. Or if we had to target a munition, again, we have to come in from this direction. So this is very operational in a lot of ways. Okay, I'm sorry I had to go so fast. I guess the key takeaway is there's a lot of information here that people are not using, and Sentinel data is free. And I think it's important that your image analysts get training in how to use the software and extract this information. Because we're to the point now where you can do this fairly automatically. A little bit of intelligent input from a human being can make this very, very valuable information. No other way to get it. Okay, thank you very much for your time.